Good morning, everyone. My name is Tomasz Kostecki, and I'm a medical physicist here at Diagnomatic. I have been working with MRI scanners for about 15 years, and I would like to welcome you to this Diagnomatic Academy presentation on fundamentals of MRI testing. If you have any questions, write them in chat, and I'll answer them at the end of the meeting. Today, I would like to share practical information on MR quality control, focusing mainly on American College of Radiology routine constancy testing, and how quality control results can help us monitor scanner performance over time. The goal is not only to understand which tests we perform, but also why these tests matter in daily clinical practice. I will briefly explain why quality control is important, how quality control results should be reported, which diagnostic products can be used, and then I will go through the main weekly test procedures. I will not be discussing annual tests or the full ACR accreditation process. First, let's start with a simple question. What is quality control? Quality control is a set of technical procedures used to make sure that the scanner continues to produce high-quality diagnostic images. It's not only something you should do after installation. Quality control also helps us establish baseline performance, detect changes in scanner performance early, and check if corrective actions have worked. An effective quality control program will not prevent every problem, but it can help identify problems before they seriously affect clinical images. This is the key point. Quality control is not only about completing forms. It's about monitoring the scanner over time and noticing changes before they become clinical problems. All quality control documentation should be kept in a central location near the MRI scanner. This allows the technologist, physicist, radiologist, and service engineer to review the results when needed. In my opinion, it is also very useful to present some parameters as charts, because trends are often easier to see visually than in a table. For example, at my first MRI site out of boredom, I started making my own Excel charts to track helium levels over time. When I looked at the trend, I noticed that something was changing. It was a possible helium leak, and in the end, that's exactly what it was. The timing was also important because it was close to the end of the year, when getting helium refill can be much more difficult. That simple chart may have helped the hospital to avoid a quench, and at the very least, it probably saved a service engineer from spending Christmas at work. Diagnomatic software combines the advantages of traditional paper reporting with the benefits of digital analysis. The data is safer than in a simple Excel file. It also makes the quality control process faster because many of the tests are performed automatically. Another important advantage is trend analysis. The software can generate charts, making it easier to see changes. Now I will move to the phantom part of the presentation. Diagnomatic provides 4 types of MRI phantoms, 2 Pro MRI ACR phantoms, certified for use with the American College of Radiology accreditation program, and 2 other Pro MRI phantoms. At first glance, they look similar, so the next few slides show the main differences and how to recognize which phantom you are using. This table compares the 4 MRI phantoms available from Diagnomatic. The older Pro MRI phantoms have slightly different design, including more vials and additional wedged structures, but they can still be useful for routine quality control. One easy way to distinguish the older Pro MRI phantoms from the Pro MRI ACR phantoms is to look at the wedge structures. The older Pro-MRI phantoms have two pairs of crossed 45-degree wedges, while the Pro-MRI ACR phantoms have just one pair. The older Pro-MRI phantoms have different internal layout from the Pro-MRI ACR phantoms. Because of this, the testing protocol is slightly different. The older Pro-MRI phantom requires 10 slices, while the Pro-MRI ACR phantom requires 11 slices. From this point onward, I will focus only on the ACR phantoms. As shown in the table, ACR phantoms are available in three sizes: large, medium, and small. We are currently working on the small phantom, so it's not yet available. To keep the presentation clear, I will omit the small phantom and focus on the large and medium ACR phantoms. This table shows how to select the right phantom for the particular MRI site. The general rule is to use the largest ACR phantom that fits inside head coil used for clinical brain imaging. The main difference between the Pro-MRI ACR phantoms is their size. Because the medium phantom is a smaller internal volume, some of its internal structures are shortened compared with the large phantom. As you can see, the wedges are a bit longer, but the main wedge is in the same position in both phantoms. Nevertheless, both phantoms can be scanned using the same general protocol, including the same number of slices, field of view, and slice thicknesses. The weekly quality control procedures include several checks: setup and table position accuracy, center frequency, transmitter gain or attenuation, geometric accuracy, high contrast spatial resolution, low contrast detectability, and the artifact evaluation. The most crucial and often the most time-consuming part of the procedure is correct phantom positioning. Diagnomatic provides several positioning aids to make this step easier and more reproducible. These include the spirit level, mounting shelves for the levels, and a dedicated cradle. The cradle can be slid directly into the head coil, reducing the need to immobilize the phantom with pads and sandbags. This makes positioning faster, more stable, and more consistent from one quality control session to the next. This image shows the phantom interior elements can be used for alignment. The phantom is correctly positioned when the laser light is aligned with the superior edge of the grid structure or geometry block, like in the middle picture. The laser is properly calibrated. If the laser is properly calibrated, this alignment will place the phantom correctly at the magnet isocenter after it's moved into the scanning position. So as you can see here, the laser just slides on the surface of the grid. After positioning the phantom, we can start the scan. First, we perform a three-plane localizer to check the general position and alignment of the phantom. After that, we perform the first ACR sequence, the sagittal localizer. It's important to remember that the three-plane localizer cannot replace the ACR sagittal localizer. The fast localizer images do not have sufficient spatial resolution for accurate axial slice prescription, phantom length measurement, or table position evaluation. The ACR provides a weekly quality control data form to help record the test results in a consistent way. This makes it easier to compare results over time and identify changes in scanner performance. The first test in this form is setup and table position accuracy. To perform this test, we use sagittal localizer image. If the positioning laser is correctly calibrated and the table positioning system is working properly, the superior edge of the geometry grid should be localized in the magnet isocenter. To check this, we place a cursor on the superior edge of the grid structure and read the superior-inferior value provided by the scanner software. If the value is within the acceptable tolerance, the table position accuracy is considered acceptable. And the tolerance, by the way, is 5 millimeters. The next test is simple console check. If the scanner computer starts normally and the user interface works properly, we just record yes in the quality control form. If there is any problem, we describe it in the notes and report it according to the local quality control procedure. The next two columns are for center frequency and transmitter gain or attenuation. These values can usually be checked directly in the scanner system or, if possible, extracted from the DICOM tags. At the moment, we have only found these values in Siemens DICOM files, as they are usually most complete. For that reason, in Diagnomatic software, these parameters can also be entered manually. Center frequency quality control is based on the weekly change in frequency and not the absolute value. In superconducting MRI magnets, the center frequency should remain very stable from week to week. The allowed change is usually expressed in parts per million or ppms. To convert this into hertz, we multiply the ppm value by the Larmor frequency in megahertz, typical for the magnets we are using. This table shows how ppm translates into hertz. For a 1.5 Tesla scanner, 2 ppm equals 128 hertz per week. For a 3 Tesla scanner, 2 ppm equals 256 hertz per week. Although in this example, total change over 3 weeks is 310 hertz. Only the week-to-week change is computed compared with the action limit. An alert is triggered only in the third week because the weekly change is 170 hertz, which is above the 128 hertz action limit. Further tests are assessed using the actual scans of the phantom. ACR accreditation uses several phantom sequences, but for weekly constancy checks, the ACR manual recommends using just ACR sagittal localizer and the ACR axial T1 weighted sequence. The next step is to plan the axial series on the sagittal localizer. The ACR protocol uses 11 axial slices. These slices should be positioned carefully using the centers of the slice locations and not the slide outlines. This is a common mistake, so remember to check that. Correct slice positioning is important because different quality control tests are performed on specific slices. If the slices are shifted or tilted, the measurement might fail even if the scanner itself is working correctly. The basic slice should be positioned at the inferior wedge, close to the chin side of the phantom, and the ACR description In the ACR description, this is usually treated as slice 1. However, depending on the scanner system and the direction in which slices are numbered, the same physical slice might appear as slice 11 on your console. So remember that. This is the start of the scanning sequence. A simple way to check correct positioning is to look at the first slice, the resolution slice. The two wedge structures should appear at the same height. If they are not equal, the slice position or phantom alignment might need correction. Geometric accuracy tells us whether the scanner measures distance correctly. This is important clinically because if the geometry is wrong, the lesion measured with the system ruler might appear larger or smaller than it really is. During follow-up imaging, this could influence the assessment of progression or remission. Also on this slide, you can see two geometry insert designs, a grid structure and a plastic block with 9 holes. Both designs are valid, but the Pro MRI ACR phantoms use the plastic block. This is the procedure for setting the window width and level for the geometric accuracy test. This is important because window width and level can change the distance, the visible distances. First, set the window width to a very narrow value. It's about 1 or 0. Then just the window level. Then adjust the window level until approximately half of the phantom fluid appears white and the other half appears black. Record that window level value. Next, set the window width equal to the recorded value and set the window level to half of that window width. So it's a complicated procedure, but if you do it correctly, you will get correct measurements. If geometric accuracy is outside the action limit, not every cause needs service immediately. First, we can check the simple things. Make sure there are no ferromagnetic objects near the imaging volume. Confirm that the scanner had enough warm-up time. Check that the receiver bandwidth is not unusually low. And of course, verify phantom and slice positioning. If the problem remains after repeating the measurement, then the likely causes are more technical, such as gradient miscalibration, magnetic field inhomogeneity, incorrect gradient offsets, or poor shimming. This usually require a service engineer. The next text is high contrast spatial resolution. This test checks whether the scanner can distinguish small structures that are close together. It is assessed on slice on the first slice of the ACR trial of the ACR axial T1 series. Note that the large and medium ACR phantoms have different number of resolutions arrays. The large phantom contains 3 arrays, while the medium phantom contains 4 arrays. In the resolution insert, there are pairs of small holes arrays. Each pair has an upper left array called UL and lower right array called LR. The UL and LR arrays meet in one corner and share one hole. The UL array is used to assess resolution in the right-left direction, while the LR array is used to assess resolution in the top-bottom direction. So in practice, we check both directions to confirm that the spatial spatial resolution is stable. The image passes if all four holes are distinguishable in one column or of the lower right array and the one row of the upper left array at the tested hole size. The measurements resolution might be different in the top, bottom, and left, right directions. This is normal. So just write down two values in columns. The measured resolution should remain stable over time. If high contrast spatial resolution changes, it might indicate a scanner calibration or stability issue. Possible causes include gradient field strength being out of calibration, incorrect eddy current compensation, poor magnetic field homogeneity, or unstable gradient amplifiers. These issues might also affect other quality control tests, so any change in measurement resolution should be discussed with the service engineer. Low contrast detectability is assessed on slices 8 to 11 of the ACR Phantom. The test objects are small low contrast discs arranged like the spokes of a wheel. Each spoke contains 3 discs, and each circle contains 10 spokes. Each LCD slice has one contrast level. For 5 millimeter slides, contrast increases from 1.4% on slice 8 to 5.1% on slice 11. It's very important that once the window and level are established for a specific scanner and slice number, they remain the same from week to week. The medical physicist selects the slice that is most sensitive to changes in scanner performance, and this slice number is recorded in the form. Low contrast detectability is then assessed by counting the number of complete visible spokes on that selected actual slice. A reduced LCD score can be caused by poor phantom positioning, incorrect slice positioning, low signal-to-noise ratio, too low acquisition matrix, excessive sharpening filters, ghosting, or other image artifacts. One practical example is slice planning. If the radiographer uses the slice outlines instead of the slice centers, the slices might be slightly shifted, and therefore some of them might disappear. So this can reduce the number of visible spokes, even if the scanner is working correctly. Artifact evaluation checks whether any new or unusual artifacts appear during weekly MRI quality control. These artifacts can be early indicators of scanner instability or hardware problems. They might be related to the receiver, transmitter, gradient system, RF coil, or even the phantom setup. For artifact evaluation, we adjust the window and level of each slice. The ACR method is to place an ROI in a bright area of the phantom, take the mean signal value, use the value as the window width, and then set the window level to half of it. For artifact evaluation, we check every slice. The phantom should appear round and not distorted. There should be no ghost images, no streaks, no abnormal bright or dark spots, and no new unusual image features. If ghosting appears, the first thing to check is whether the phantom is stable in the RF coil and cannot move or vibrate. So you can just add some more sandbags or add add a strap to position the phantom, and then do another scan. Okay, and now for the final thought. Unlike a CT scanner, an MRI scanner cannot simply be switched off while waiting for a crucial part. Even when it's not scanning, it's still generating costs. This is why regular quality control is important. It helps us detect changes early and may show which component is becoming unstable. That means service and maintenance can be planned before failure occurs. So in MRI quality control, it's not only about image quality. It's also about reducing downtime, controlling costs, and protecting diagnostic confidence. Here are some links for the materials I used. It's all on the ACR web pages. Okay, and thank you.